This is video number 3 for Computer Science 2124. Isn't it, child? Don't run into my easel. And I'm sure you'll recall from last time that what had we just done? We had just decided to set up a class invariant. I heard you that time too. No, we did not. Well, okay, you win. Here's an aside. Definition. An important definition. I'll have to remind myself not to say important. All this is important. Class invariant. A class invariant is a rule. It's a rule for ourselves as we are developing a class, a type of objects implementing an ADT. A class invariant is a rule that, couple of things, all member functions except the constructor get to assume on entry. That means whatever we've listed as a class invariant, for example, the head pointer points at the empty head node. When I call the get operation or the insert operation or any of the other operations, any of the other member functions, even the destructor, when it's called for me automatically, they get to assume that that rule is in place, it's been enforced. Another thing, all member functions except the destructor still not used to this wiggly whiteboard. All member functions except the destructor must ensure, E-N-S-U-R-E, must ensure on exit. If I'm going to underline ensure down here, I'm going to underline assume up here. Let me put those two together. Let's focus on the get function. We don't have a lot of member functions to focus on, but the get function does not have to test. If we've said it's a class invariant, that the head pointer always points at some node, even if it's got garbage data or whatever, the head pointer is not going to be 0 no matter what. Then the get function is excused from having to test to see if the head pointer is 0 before it does whatever it's got to do. It gets to assume that for free. Now, it's a two-edged sword. The get function, or maybe the insert function, whatever, any of those functions that have assumed that, they might temporarily violate that. I can't think of a reason why they would, but if somebody decides, you know what, I've really got to set the head pointer to 0 to be able to get my work done, then they have to make sure that they fixed it before they hit their own closing curly bracket. In other words, they get to assume it for free without testing it, but they also have to keep that true, set it up for the next member function that's called, by ensuring that that class invariant is true before they exit. I almost said ensure it's still true, which makes it sound like it has to be truthfulness true all the way through the member function. That's not true. The truthfulness is not true. It could be there's some minor surgery that goes on inside the member function that temporarily violates a class invariant, but they have to make sure that all the class invariants are met before they hit their closing curly bracket. What that does, it makes all these member functions' lives easier. There's fewer things they have to test. If I get to assume, without testing, that the head pointer is not 0, then I don't have to check and see if it's 0. I don't have to check and see if the list is empty. So that's the one and only one class invariant we've looked at so far. Class invariant for our linked list. To make it look official, I'm going to put it in double quotes. The head pointer always points at some node in the list. Where remember the head pointer, at this point at least, is our one and only one private variable. It's our only state variable. The head pointer must point at some node in the list. It's never 0. It's not garbage. How did we ensure that? Well, I'll review the picture for you. here's the constructor pictorial design. Before, we've got the head pointer itself, which we get for free. There's no dynamic memory allocation involved there. We declare that as a pointer to a structure. A standard name for that structure is a node structure, which is very generic, meaning it'll hold any kind of data. So we've got a pointer to a node structure called head in the private section of our header file for the linked list class. You with me on all that? That refers back to all these things we've done with classes so far. Initially, that's garbage, just because there's not any way to avoid that. But the after picture, after our constructor gets a hold of it, gets control and does what it's going to do, then I'm going to suggest, without giving an awful lot of justification or explanation at this point, we're going to go ahead and dynamically allocate a node. Even though nothing's been inserted in the list yet, we'll dynamically allocate a node with garbage data, and a 0 is the next pointer. Why? So that none of the other member functions have to test and see if the list is empty. It almost seems like cheating, doesn't it? The list is never empty. I'm sorry, I'm going to have to end this video right here. I got a phone call coming through. I forgot to turn off my phone. Sorry about that. This is a continuation of video 3, so I didn't set this up as a separate video. Here's what we got. Here's the before picture. Here's the after picture. What's missing? Trout, no! What's missing are the steps of the algorithm. How are we going to do this? And I do this for completeness. We're going to have steps and pictures before and after for all of them. But step 1, we got that for free. There's nothing to do there. I'm going to say allocate the empty head node. Allocate empty head node. That's the first step of going from the before picture to the after picture, and that's why we have pictures. So we've got something to refer to and make sure we don't leave anything out. Have I left anything out? Well, I don't have any data to put in there, but I do need to do this. Set head arrow next to 0, because that doesn't happen automatically. Set head arrow next to 0. So we have a way to automatically test and see when we're at the end of this list. Which actually, now that we've done that, I'm going to go ahead and tighten up my class invariant. This is good. The head pointer must always point at some node in the list. But again, flash back to the list of cats, the list of athletes. Not only does the head node need to point at some node in the list, it's going to need to point at this empty head node for the rest of its natural life. In other words, we've got to have this anchor that's always going to point to the first node in the list. So I'm going to call this, with a different color, a revised class invariant. I'll abbreviate invariant. We in the biz might call this a refactored class invariant. We've gone back and basically got the same outcome, but we found a better way to state it or a better way to do it. The head node must always point at the first node in the list, which is the empty head node. Stated more briefly, head must always point, double, always, don't move it, must always point at empty head node. Hope that's not too far off the board. Yeah, you can probably see that. A tighter, more specific class invariant. And ladies and gentlemen, we now have us a linked list. It doesn't have any data in it whatsoever, but we do have a linked list to set up. Now, let me see. Is this a good stopping point? I've got other stuff going on, unfortunately. I could slip in the destructor. You might think I can't, but I can. Why? Because I'm going to procrastinate on it. Our operation 2 of our wish list of ADT operations was the destructor. I'm going to procrastinate and just say later. Why? Well, for one thing, the destructor is the absolute last thing that's going to be executed. Another thing that's more important in this discussion is we don't even know what all we're going to have to destroy yet. This hasn't gone through a normal life cycle of a linked list, so the destructor would be premature to even draw before and after pictures or anything. We don't know what's going to be there. We don't know what we're going to have to destroy. And that actually, I think, is a natural ending place for video 3. This was a 2-part video. Sorry about that. But anyway, onward. See you online.